Integration by parts looks like a trick the first time you see it. One function wears a little hat called U, another function gets called dv, and suddenly an integral has changed costumes. But underneath the notation, there is a picture. Imagine a point sliding along a curve. As it moves right, a rectangle grows with it. Its width is x, its height is y. The rectangle is not mysterious. It is just width times height. No wizardry, no fog machine, just a rectangle minding its own business. Now here is the question. If the rectangle changes as the point moves, where does its new area come from? Some area is added because the rectangle gets wider. Some area is added because the rectangle gets taller. The rectangle has two ways to grow. Integration by parts is the bookkeeping that keeps those two kinds of growth from getting mixed up. This symbol looks scary like taxes, but it is mostly just bookkeeping. Let us start with a curve rising gently from left to right. Pick a moving point on it. Drop a vertical line to the x-axis and a horizontal line to the y-axis. Together they make a rectangle. The full rectangle has area x times y, but the curve cuts the rectangle into two visual pieces. One piece lives under the curve. The other piece lives to the left of the curve if you think of x as a function of y. Those two pieces fit together perfectly. They fill the rectangle, so visually, rectangle area equals area under the curve plus the sideways area beside the curve. That is the whole secret. The formula will come later wearing a blazer. When x increases a tiny bit, the rectangle gains a thin vertical strip. That strip has height y and width dx. Its area is y dx. When y increases a tiny bit, the rectangle gains a thin horizontal strip. That strip has width x and height di. Its area is x di. The small corner where both change is tiny twice over, so it fades away in the limit. The rectangle grows in two main directions, so the change in xy is y dx plus x dy. That is the product rule in a picture. The arrows are not confused. They are just going through a transitional period. Now stretch this tiny idea across a whole interval. As the point travels, all the vertical strips pile up under the curve. Their total is the integral of y dx. The horizontal strips pile up sideways. Their total is the integral of x dy. Together, they make the difference in rectangle area from the start to the end. This is the bridge. Integration by parts is the product rule, accumulated over time. The product rule says how a product changes in one instant. Integration by parts says how the accumulated pieces must balance over an interval. Now we can name things. Let U be one changing quantity. Let V be another. Their rectangle has area UV. When the rectangle grows, part of the change is V du. The other part is U dV. Accumulating both pieces gives the change in UV. So the integral of U dV plus the integral of V du equals UV. More precisely, across an interval, it equals the endpoint change of UV. Move one piece to the other side, and the famous formula appears. The integral of U dV equals UV minus the integral of V du. This is where the math stops wearing a hoodie and puts on a little blazer. But notice what happened. The formula did not appear from nowhere. It is the same rectangle picture compressed into symbols. Now a short pause from the math. If you want to learn more math like this, check out Zetaflow on the App Store. It's an app to learn advanced math on your free time, with new chapters coming out consistently, and I take requests for lesson plans. Link in bio. Back to the rectangle. Why is this useful? Because sometimes the integral you have is a messy, swept area, but the partner area is easier. You trade one accumulation for another, not for free. Math is old enough to know better than that, but for a price you can see, the boundary rectangle UV. Let us work through a classic example, the integral of x times cosine x dx. Here the x part is a slowly growing height label. The cosine part is the motion that creates a sine curve when accumulated. Choose u equals x, choose dv equals cosine x dx, then du equals dx, and v equals sine x. The boundary rectangle becomes x sine x. The leftover partner area becomes the integral of sine x dx. So the original integral is x sine x minus the integral of sine x dx. And that leftover integral is negative cosine x. Subtracting it gives x sine x plus cosine x. Add the constant at the end, because indefinite integrals always keep a spare key under the mat. Now watch the visual meaning. The original area asks for cosine waves, whose contribution is scaled by x. Farther to the right, the waves matter more. Integration by parts trades that weighted cosine area for a boundary term and a simpler sine area. The difficult part gets transferred from the oscillation onto the simpler changing factor. The usual classroom advice is to pick u as the thing that gets simpler when differentiated. Polynomials are friendly here. Differentiate x and it becomes 1. Differentiate x squared and it becomes 2x. They gradually calm down, like someone lowering the volume on an old radio. Meanwhile, dv should be something you can integrate. Cosine becomes sine. Exponential stays exponential. Logarithms often become simpler once they are differentiated. For example, the integral of ln x dx looks impossible at first because there's only one visible factor. But you can secretly write it as ln x times dx. Let u be ln x and dv be dx. Then du is 1 over x dx and v is x. The formula gives x ln x minus the integral of x times 1 over x dx. That leftover integral is just the integral of 1 dx. So the answer is x ln x minus x plus a constant. The trick was not magic. It was choosing the rectangle so one side became simpler. This idea appears all over advanced math. In differential equations, it moves derivatives from one function onto another. In Fourier analysis, it explains why smooth functions have rapidly shrinking frequency coefficients. In physics, it turns local change into boundary information. In machine learning, cousins of this idea show up whenever gradients are shifted through a loss or an expectation. Different rooms, same furniture. The bigger picture is this: an integral is not always a thing you attack directly. Sometimes you ask what other area completes the rectangle. Sometimes the missing piece is easier to measure. And sometimes the boundary tells you more than the interior. So when you see integration by parts, do not start with the symbols. See a growing rectangle, see the vertical strips, see the horizontal strips, see the two accumulated areas sharing one boundary. Then the formula becomes almost unavoidable. The area you want equals the boundary rectangle minus the partner area. That is integration by parts. It is not a trick. It is the product rule turned sideways, accumulated, and drawn as a rectangle.